Hello, sir. I have prepared a PowerPoint presentation to explain better. This presentation will be like summary. I would like to start with description of harmonics. Harmonics are unwanted high frequencies which superimposed on the fundamental waveform, creating a distorted wave pattern. Harmonics and harmonic distortion is the difference between the ideal sinusoidal waveform, the supply voltage, or the load current waveform should look like, and what it really is as a result of a nonlinear load. In an electrical or electronic device or circuit that has a voltage current characteristic which is not linear, that is, the current flowing through it is not proportional to the applied voltage. The alternating waveforms associated with the device will be different to a greater or lesser extent to those of an ideal sinusoidal waveform. These types of waveforms are commonly referred to as non-sinusoidal or complex waveforms. Complex waveforms are generated by common electrical devices such as iron core inductors, switching transformers, electronic ballasts in fluorescent lights, and other such heavily inductive loads, as well as the output voltage and current waveforms of AC alternators, generators, and other such electrical machines. The result is that the current waveform may not be sinusoidal, even though the voltage waveform is. Graphics of harmonic and complex waveforms. I would like to show these graphics like this. Note that the red waveforms above are the actual shapes of waveforms as seen by a load due to the harmonic content being added to the fundamental frequency. The fundamental waveform can also be called a first harmonics waveform. Therefore, a second harmonic has a frequency twice that of the fundamental. You can see over here F and 2F. And the third harmonic has a frequency 3 times the fundamental, and a fourth harmonic has 4 times the fundamental as shown in the left hand side column. We can see that a complex wave is made up of a fundamental waveform plus harmonics, each with its own peak value and phase angle. For example, if the fundamental frequency is given as given as like this, the values of the harmonics will be given as like we can find the harmonic like this equation. I would like to continue with harmonic distortion. Harmonic distortion refers to the presence of unwanted frequency components, known as harmonics, in an electrical signal. Harmonics are integer multiples of the fundamental frequency and can cause various issues in power systems and electronic equipment. Harmonic distortion occurs when nonlinear loads, such as power electronic devices and nonlinear loads, introduce additional frequency components beyond the fundamental frequency. Harmonic distortion can have several adverse effects. It causes voltage and current waveform distortions, leading to distorted waveforms with irregular shapes. This distortion can result in increased losses, reduced efficiency, and decreased power quality. Harmonics can also lead to overheating of equipment, especially transformers, capacitors, and cables, due to increased circulating currents. Additionally, harmonic currents can interfere with communication systems, affecting the reliable operation of sensitive equipment. To assess harmonic distortion, several indices and measurement techniques are used. The total harmonic distortion is a commonly used metric that quantifies the overall harmonic content in a signal. I gave information and formulas about total harmonic distortion in my file, in my test, sir. Other indices, such as individual harmonic distortion levels, can provide more detailed information about specific harmonic components. Mitigating harmonic distortion involves various techniques: passive filters, such as harmonic filters and tuned filters, provide a low impedance path to divert harmonics away from sensitive equipment. Active filters, on the other hand, use power electronic devices to actively cancel out harmonic currents. Hybrid filters combine both passive and active filtering approaches for improved performance. Advanced control algorithms and emerging technologies are also being developed to enhance harmonic mitigation. In summary, harmonic distortion is the presence of unwanted frequency components in an electrical signal. It can lead to voltage and current waveform distortions, increased losses, equipment overheating, and interference with communication systems. Effective mitigation techniques, including passive and active filters, are employed to minimize harmonic distortion and improve power quality in electrical power systems. I would like to tell about the effects of harmonic distortion in power systems too, sir. Harmonic distortion in power systems can have various adverse effects on power quality, equipment performance, and overall system reliability. Here are some key effects of harmonic distortion. First one, voltage and current waveform distortion. Harmonic distortion causes irregularities in voltage and current waveforms, leading to distorted wave shapes. This distortion can result in high peak voltages, blood tapping or notching of waveforms, and waveform asymmetry. These waveform distortions can affect the operation of sensitive equipment and lead to inaccurate metering and control. Increased power losses. Harmonic currents circulating through power system components such as transformers, cables, and capacitors result in increased resistive losses. These additional losses can lead to reduced energy efficiency, increased operating costs, and premature aging of equipment. And one of effects is overheating of equipment. The presence of harmonic currents in power systems can lead to increased heating in equipment. Transformers, cables, and other components may experience elevated temperatures due to the additional energy dissipated by harmonic currents. Overheating can reduce the lifespan of equipment, degrade insulation materials, and increase the risk of failures and breakdowns. Resonance and amplification. Harmonic frequencies can interact with the natural resonant frequencies of power system components, leading to resonance effects. Resonance can cause voltage amplification, voltage distortion, and increase stresses on equipment. This phenomenon can result in equipment malfunctions, equipment failures, and voltage fluctuations. Interference with communication systems. Harmonic distortion can generate electromagnetic interference that affects communication systems. The presence of harmonic currents can disrupt the operation of sensitive electronic devices, leading to data transmission errors, signal degradation, and communication system failures. Non-compliance with standards. Harmonic distortion can violate power quality standards and regulations established by utility companies or governing bodies. Utilities may impose limits on harmonic levels to ensure the quality of power supply to consumers. Non-compliance with these standards can result in penalties, regulatory issues, and strained relationships between utilities and customers. It's crucial to address harmonic distortion in power systems to mitigate these effects. The implementation of harmonic mitigation techniques such as passive and active filtering helps to minimize harmonics, improve power quality, and maintain the reliable operation of electrical equipment. Harmonic mitigation in power systems. Harmonic mitigation is in power systems involves implementing various techniques and strategies to minimize the effects of harmonic distortion. Here are some commonly used methods for mitigating harmonics. Passive harmonic filters. Passive filters are designed to provide a low impedance path for harmonic currents to flow, diverting them away from sensitive equipment. These filters consist of inductors, capacitors, and resistors that are tuned to specific harmonic frequencies. Passive harmonic filters are effective in reducing harmonic distortion but are